Students and friends, today we are going to discuss the new topic, that is NMR spectroscopy. NMR spectroscopy is much recent technique, and before discussing about its introduction or principle, we will discuss about the history of NMR spectroscopy. This technique is introduced or discovered after 1945. In 1945, the phenomenon of NMR spectroscopy was simultaneously studied and discovered by two groups of scientists. First is Purcell, Torre and Brown at Harvard University, Paraffin, and the another group of scientists is Bloch, Hansen and Packard at Stanford University, Water. In 1950, the first NMR spectra of ethyl alcohol was recorded by Arnold, Dermody and Packard, while in 1952, the two discoveries was awarded the first Nobel Prize in nuclear magnetic resonance spectroscopy in physics, and this Nobel Prize is awarded to Bloch and Purcell. In 1991, the second Nobel Prize in NMR spectroscopy was awarded in chemistry to Richard Ernest for discoveries of advanced methodologies, while in 2002, the third Nobel Prize in NMR spectroscopy in chemistry was awarded to Kurt Woodrich for determination of structure of biomolecules in solution by nuclear magnetic resonance spectroscopy, while in 2003, the fourth Nobel Prize is awarded in medicine, and it is awarded to Paul Lutterberg and Sir Peter for magnetic resonance imaging. We have studied in detail electromagnetic radiations. We have also studied ultraviolet and visible spectroscopy, its applications in determination of unsaturation or functional groups present in a molecule. In electromagnetic radiation, which consists of gamma rays, X-rays, ultraviolet radiations, visible radiations, infrared region, microwave radiations and radio wave radiations. Along these different regions, the wavelength of radiation goes on increasing from gamma rays to radio waves, and therefore the frequency as well as energy of radiation goes on decreasing in this direction. Here a spectrum of visible radiation is shown, which lies between 400 to 800 nanometer. While introducing NMR spectroscopy, the nuclear magnetic resonance spectroscopy is a most recent and powerful analytical technique used to characterize organic molecules by identifying carbon-hydrogen framework in a molecule. The common types of NMR spectroscopy are used to characterize organic molecule is proton magnetic resonance spectroscopy, and it is used to determine the type and number of hydrogen atoms present in a molecule. The another type of NMR spectroscopy is known as C13 NMR spectroscopy, and it is used to determine the type of carbon atoms in the molecule. The source of energy in NMR spectroscopy is radio frequency region, that is radio waves, which have longer wavelengths. Therefore, it has low energy and less frequency. When these low energy radiations of radio waves interacts with molecule, they can change the nuclear spin of some elements, including hydrogen and carbon, that is C13. Here you will see a nuclei. The some basics about the NMR phenomenon by classical perspective is shown here. That is, a nuclei which is spinning along its own axis in random motion. But we know that the nuclei of an atom contains protons and neutrons in its nucleus, while electrons, they are revolving in a specific orbit around the nucleus. That is, each nuclei is a charged particle. Therefore, while spinning along its axis, this charged particle generates a magnetic moment mu along its axis of spinning. Therefore, the magnetic nuclei behaves like a microscopic bar magnet. Here, the microscopic bar magnet nature of a spinning nuclei is shown, which generates the magnetic moment. A nucleus with an odd atomic number or an odd atomic mass number has a nuclear spin, and the spinning charged nucleus generates a magnetic field. Here in this figure, it is shown that this nuclei is spinning along this axis, and due to this spin, the magnetic moment generated by this nuclei shows a loop of current which is flowing around the nucleus in this direction, and therefore it acts as a bar magnet, which is shown here. That is, every charged particle moving around its own axis under the influence of externally applied magnetic field acts as a bar magnet, which is shown here in this animation. If you observe the axis of rotation of this spinning nuclei, that is a charged particle, and therefore it acts as a tiny bar magnet. Hence, when such a tiny bar magnet or a charged particle spins around its own axis under the influence of externally applied magnetic field, its behavior acts as a nuclear magnet in a magnetic field H0. Here in this figure, it is shown that this type of motion of a charged particle under the influence of externally applied magnetic field is known as precessional motion, and the orbit through in which it is rotating or spinning is called as precessional orbit under the influence of externally applied magnetic field, and it generates magnetic moment due to its spin along this spinning axis as mu. Here, each charged particle or nuclei under the influence of externally applied magnetic field has two values, that is plus 1/2, that is alpha state, which is aligned with externally applied magnetic field, called as low state or lower energy level, while the another value is minus 1/2, it is spinning aligned against the direction of externally applied magnetic field, and called as beta state, that is high energy state. When a charged particle such as a proton spins on its axis, it creates a magnetic field. Thus, the nucleus can be considered to be a tiny bar magnet. We know that normally these tiny bar magnets are randomly oriented in space in all directions. However, in the presence of externally applied magnetic field, that is B0, they are oriented with or against the externally applied magnetic field. More nuclei are oriented with the applied magnetic field because this arrangement is lower energy level. That is, the magnetic moment generated by a spinning nuclei aligned parallel to externally applied magnetic field. Here it is shown that in this figure a spinning proton creating a magnetic field, and with no externally applied magnetic field their spinning axis is like this in random motion. The nuclear magnets are randomly oriented in space in all directions. But when the same nuclei, when come under the influence of externally applied magnetic field B0, then in presence of such externally magnetic field, the nuclear magnets are oriented with or parallel to the externally applied magnetic field. Otherwise, it may orient in anti-clockwise direction or against the direction of externally applied magnetic field. That means every nuclei or every bar magnet generates two states. One is high energy state and another is low energy state. The low energy state is designated by alpha having spin quantum number I is equal to +1/2. While nuclei which orients against the externally applied magnetic field has the spin quantum number -1/2 and denoted by the symbol beta state, which is high energy state. In the absence of magnetic field, spins are oriented in random, which is shown here in this figure. Every nuclei is spinning along its own axis and they orient in any direction or in many directions. But under the influence of external applied magnetic field, the spinning nuclei spins along its axis, around its axis, but while spinning, it may orient either parallel to externally applied magnetic field in this direction or either anti-parallel in this direction to externally applied magnetic field. So this state is alpha state and this state is beta state. In the presence of H0, each spin or magnetic moment vector can have two orientations. In a magnetic field, there are now two energy states for a proton. The low energy state with the nucleus aligned in the same direction as H0 or B0, and a higher energy state in which the nucleus aligned against H0. When an external energy H nu, which matches the energy difference delta E between the two states of nuclei, is applied, then energy is absorbed by the molecule or absorption of energy takes place, which causes the nucleus to spin flip from one orientation to another orientation. The energy difference between these two nuclear spin corresponds to the low frequency radio frequency of the electromagnetic spectrum, and thus the two variables characterize nuclear magnetic resonance spectroscopy. An applied magnetic field H0, the strength of which is measured in Tesla. It is a unit to measure strength of applied magnetic field, and the frequency n of radiation used for resonance. It is measured in hertz or megahertz. Usually 1 megahertz is equal to 10 raised to 6 hertz. A nucleus is in resonance when it absorbs radio frequency radiations and spin flips to a higher energy state. The low energy state nuclei and high energy state nuclei, the energy level difference is very, very small. Delta E can be calculated by using the equation delta E is equal to h nu. By absorbing h nu amount of energy from radio frequency radiation, it causes flipping of spin. That is, nuclei get excited from lower energy level to higher energy level. The basic of NMR equation. For a proton spin, I is equal to 1/2. There are 2I plus 1 possible orientations. These two possible orientations may be the energy of orientation is a product of magnetic moment mu and strength of applied magnetic field H0. Therefore, energy of the molecule E can be calculated as E is equal to mu into H0, where mu is the magnetic moment generated by the spinning nuclei and H0 is the value of externally applied magnetic field. The nuclei in the state aligned with the externally applied magnetic field is represented low energy level orientations, and its energy E1 can be calculated as E1 is equal to minus mu into H0. While if the nuclei is aligned against the externally applied magnetic field, then it indicates high energy level orientation and it has the value of spin quantum number I is equal to minus 1/2, and energy of the nuclei E2 is calculated as E2 is equal to plus mu H0. Therefore, the delta E, that is energy level difference between these two states, can be calculated as delta E is equal to 2 into mu into H0. As E is equal to h nu, at a resonance, h nu is equal to 2 into mu into H0, as nu is equal to 2 mu H0 upon h. The equation is written as nu is equal to rho into H0 divided by 2 pi, where in this equation rho is equal to 2 pi mu upon h into I. It is a proportionality constant between magnetic moment generated by spinning nuclei mu and the spin quantum number I, also called as gyromagnetic ratio or gyroscopic constant. It is constant for a particular nuclei but different for different nucleus. The frequency needed for resonance of the nuclei and the applied magnetic field strength are proportionally related by the equation nu is equal to K into B0 or H0. That is, frequency of radiation is directly proportional to B0. If stronger is the magnetic field, then the larger the energy difference between the two nuclear spin states, and the higher is the value of nu needed for resonance. We know that NMR spectrophotometers are referred to as about 300 megahertz instruments or 500 megahertz instruments, and so depending upon the frequency of radio frequency radiations used for resonance, these spectrophotometers use very powerful magnets to generate a small but measurable energy difference between two possible spin states of a spinning nuclei, and it can be measured easily. Now, while discussing about instrumentation in NMR spectrophotometer, here a schematic diagram is shown in which here there are two strong bar magnets. This one and this one, these are the magnetic poles, that is magnetic bar magnets used to apply externally applied magnetic field, and these are the sweep coils within which a sample is kept in the sample cell, and this is the coil. Spinning sample tube is kept in between this strong magnetic field, and it is associated with radio frequency receiver and amplifier, which is attached to control console, that is a recorder. In simple words, it is computer. The radio frequency transmitter generates the radio waves which are absorbed by the sample under testing, which is kept in the sample cell, and the signal is passed to this receiver, which amplifies the signal and given to the recorder. So this is the simple schematic block diagram for arrangement of components of nuclear magnetic resonance spectrophotometer. Here the NMR spectrophotometer, the modern picture is shown for your illustration. The sample is dissolved in solvent in a thin NMR tube and placed in a strongly applied magnetic field in this chamber. In this chamber, the strongly applied magnetic field, indicates the cross section of this chamber, in which here in a sample cell the compound under study is filled and it is kept in this cylinder or chamber we call, which is under the influence of strong externally applied magnetic field. This is a superconducting magnet. In the NMR probe, the sample is rotated in a magnetic field and irradiated with a short pulse of radio frequency radiations. This NMR console, and it is attached to the receiver, which gives signal to this recorder where NMR spectra can be recorded. The sample is dissolved in solvent. Usually, the solvent used is CdCl3, that is deuteriochloroform, or solvents which do not contain hydrogen atom are usually used in NMR spectroscopic technique and placed in a magnetic field. A radio frequency generator generates radio waves and it is irradiated the sample with a short pulse of radiation causing resonance. When the nuclei fell back to their energy state, the detector measures the energy released and the spectrum is recorded by recorder. The superconducting magnets in modern NMR spectrometer have coils that are cooled in a liquid helium and conduct electricity with essentially no resistance. Here is a very modern instrument which is used as a nuclear magnetic resonance is shown in this picture. Protons in different environment absorbs at slightly different frequencies. So they are distinguishable by nuclear magnetic resonance spectroscopic technique. The frequency at which a particular proton absorbs it's determined by its electronic environment. That is, the frequency at which a particular proton shows absorption of infrared radiation can be determined by its electronic environment, the size of the magnetic field generated by the electrons around a nucleus, and a proton determines where it absorbs. The modern NMR spectrometers use a constant magnetic field, that is B0, and then a narrow range of frequencies is applied to achieve the resonance of all protons, where only nuclei that contain odd mass numbers such as H1, C13, F19 or phosphorus 31, or the nuclei which are having odd atomic mass numbers such as H2 and N14 give rise to NMR signal. That means the nuclei which are having spin quantum number in fraction gives the NMR signal. The induced magnetic field by spinning of a nuclei is shown in this picture under the influence of externally applied magnetic field B0, and the downward arrow indicates that it is the axis of spinning of this nuclei around its own axis, and this space indicates the electron density, where electrons are revolving around this nucleus in a specific orbit. The nuclear magnetic resonance spectroscopy gives the spectrum which is shown here for ethanol. In case of ethanol, we know that ethanol molecule possesses 3 different types of protons, where here in this spectrum one signal is observed here which is for one of the type of hydrogen atom. Here there is another signal, and here is the third signal. The signal appeared at this 4 delta value, this delta value on delta scale 4, it indicates the presence of OH hydrogen atom, that is hydrogen atom attached to oxygen atom, while this signal indicates CH2 group, that is methylene group, while this signal indicates the presence of CH3, as the chemical environment of these three types of protons, that is protons present in methyl, methylene and hydroxyl group, they have different chemical environment, and because of this different chemical environment they shows three signals, where here in this signal it is divided or appeared as a triplet. This signal it appeared as a quartet, while this signal given by hydrogen atom of hydroxyl group, it appears as a sharp singlet. In H1 NMR, the spectrum observed is as shown in following figure. An NMR spectrum is a plot of the intensity of a peak against its chemical shift. That means along this axis, y-axis, intensity of peak is shown. Along the x-axis, the chemical shift values are there in delta scale or tau scale. Along this direction, the chemical shift value goes on increasing in ppm in delta scale. So here there is 10 delta, while here it is 0 delta. At 0 delta, the reference standard used in NMR spectroscopy is TMS, where TMS is tetramethylsilane, which contains 12 equivalent protons, and all these 12 equivalent protons, they shows a sharp signal on delta scale, which is recorded as a 0 delta, and around this 0 delta, from this 0 delta, all other protons present in a molecule shows their absorption in the range up to 10 delta. So as delta value increases, the protons are called as downfield protons or in downfield direction, while if delta value is 0 at TMS, then it is called as upfield proton or upfield direction. Increasing chemical shift values along this delta scale shows different peaks depending upon the chemical environment of each type of proton. Here in this spectrum of a ketone, different signals are shown. This is the signal shown by TMS. This is the signal shown by methyl protons of tertiary carbon atom. That is, these three methyl groups attached to this carbon atom, 9 equivalent protons are there, and therefore its intensity is very high. While the methyl group attached with oxygen atom, the signal is shown here in this compound. In H1 NMR, the spectrum NMR absorption generally appears as a sharp peak. Increasing chemical shift is plotted from left to right, that is from 0 delta value to 10 delta value, and most protons absorb between 0 to 10 ppm. The terms upfield and downfield in NMR spectrum describes the relative location of different peaks. Upfield side means to the right side, that is near to 0 delta value, while downfield side means downfield region and it orients towards the left side of this scale near to 10 delta value. The NMR absorptions are measured relative to the position of reference peak at 0 ppm and the delta scale due to tetramethylsilane. This TMS is a volatile compound. It is inert chemically and gives a sharp signal at 0 delta value in a field side of this scale. Therefore, this typical signal is considered as a 0 delta value in NMR absorption. So, we'll stop here today. Tomorrow, we will discuss in detail principle and theory of NMR spectroscopy. Thank you.